Hi, Dr. Topcu. Can you hear me?
Yeah.
Yeah. Uh, yeah. Thank you for joining us. Could you just give me a minute? I'll allow you to share the screen. Yeah, you should be able to share your screen now. Could you please check it once? Yeah. And just for your information, this is gonna be streamed live onto YouTube, and the questions on the YouTube will be on via the comments, and I can just pass on them to you whenever they come up. Yeah. And yeah, and Andreas is also attending this lecture on the stream, so he may not be joining the meeting, but he'll be still looking at the lecture. And yes, yeah, I think we can start now. Um, Hello, everyone. Welcome back to the DDLC seminar series organized by the IDS Lab at Cornell University. And I'm Nishant, and today I'm honored to introduce our speaker, Dr. Ufuk Topcu from University of Texas, Austin. A little about Dr. Topcu. He's currently the W.A. Tex Moncrief Chair in Computational Engineering and Sciences, and he's also associated as a core faculty member at the Oden Institute for Computational Engineering and Sciences and Texas Robotics, and director of the Autonomous Systems Group. Dr. Topcu obtained his PhD from UC Berkeley, and before joining UT Austin, he was at the University of Pennsylvania's Department of Electrical and Systems Engineering. And Dr. Topchu's research focuses on theoretical and algorithmic aspects of the design and verification of autonomous systems, typically at the intersection of formal methods, reinforcement learning, and control theory. And Dr. Topcu leads several large-scale projects, including an Air Force MURI project, a NASA ULI project, and an NSF CPS Frontier project. His research has garnered him the NSF Career Award in 2017 and the IEEE Control System Society Antonio Robotti Young Researcher Prize Award in 2020. And in 2021, he received the Odin Institute Distinguished Research Award. And in 2024, he was named an IEEE Fellow. And without further ado, I'll let Dr. Topchu take on talk.
Thank you for the introduction and thanks for having me. All right. So the title says it. The talk is about problems at the intersection of controlled learning and formal methods that are motivated by challenges or opportunities that we see in autonomous systems. So let me get into it. So there's a hypothesis in this talk. I want to show you evidence that this hypothesis may be valid. So learning typically relies on data, and I guess abundance of data is partially responsible for the recent advances in learning. But I want to say that if we couple data with existing knowledge, and we'll talk about how it may be represented, existing knowledge, data and knowledge together would yield some desirable properties in the learning process or the outcomes of this learning process. It might be more data efficient. We may be able to get better generalization, robustness, verifiable, etc. So this way of thinking, I'm going to build towards a couple of examples, two of which are shown here. I picked these because I have videos for them. On the left, work of a former group member with Toyota Research Institute is shown. And this is going to be, he was able to go and collect only 3 minutes of driving data. And out of that figure out how to maneuver autonomously these drifting maneuvers that the picture shows. On the right is a compositional learning algorithm where this algorithm allows for quick adaptation of the learning artifacts, even when the working environment actually changes partially. It allows to locate where the changes were and guides into what kind of adaptations take place. And the way that we evaluate these things, or the reason that we work on it, is the need for autonomous systems to be able to adjust to the changes in the environments quickly. Okay, so we'll build toward these kinds of examples. And how do we approach these questions? It is typically in the intersection of a couple of fields. And there's a reason for this. I believe that problems worth looking into, or interesting problems, challenging problems in autonomy, are beyond the perspective or tools of individual fields. We often realize a problem because thinking only within the realm of an individual field falls short, and then we have to get inspiration, or we have to create hybrid solutions at the intersection of various fields. I list 3 of them here. It is just that these 3 have been closer to my heart. By no means I claim that these 3 are the only 3, but we typically look for problems and solutions at the pairwise intersections of learning, formal methods, and control theory. And whatever I discuss today is going to very likely be, again, at pairwise intersections of this line of theory. Before I go and dive into the main body of the talk, I want to have a disclaimer. I said this is the main hypothesis here, and of course we are not the only ones who follow toward that hypothesis. That there are many different ways of interpreting the hypothesis and acting on it and trying to create evidence in many different ways. Some of the names that you might have seen include contextual inference, inductive biases, how we can incorporate inductive biases into learning algorithms. I think physics information learning is along these lines, as well as neurosymbolic AI. And so there is a spectrum of ways we can look into the hypothesis, and there is a spectrum of representations of knowledge we have, models we have, and the learning process itself. And so what I'm going to do today is I will try to, as much as I have time, I will try to go through a spectrum of things. And it is just that this hypothesis has many different faces. So as I go through these examples, I have never been able to go through 4 of them. Let's see how many of them I can go through. But the flow is that we need to use different modeling frameworks. We need to represent the knowledge differently. We need to represent what we expect out of the system differently. And even the data itself might come in different forms and shapes. And a unifying factor is going to be, in all these examples, I will be looking into sequential decision-making problems. So I'll start with this one. It is relatively old, but for the sake of having the spectrum, I think it's a good starting point, and it is a very interesting and challenging problem. So this first piece is going to follow these 2 papers. I think that the titles are relatively fun. Learning how to reach, swim, walk, and fly in one trial. And the motivation here is really how do we figure out enough about the underlying dynamics to influence the behavior of the system only in one trial. And there is a reason for it. Early on, the motivation was, what if your autonomous system goes through an unexpected, abrupt change that you had not accounted for? and you all of a sudden are facing now a system with dynamics that you had never anticipated. And one example is the part of a wing of an aircraft, for example, falling off a major subsystem of an autonomous air vehicle or any other vehicle not functioning as expected. And it is beyond hoping that you may be able to easily morph what you already know about the system to the new configuration. The changes are abrupt and there's a discrete jump. There's no possible way of smoothly adapting the dynamics or the knowledge that you have. So toward that end, here is a little setting that we're building on. We have a differential equation, and the red parts are unknown. The input appears in that form. It could be affine, but it can also be there might be a polynomial dependence on it. This is so that is the form that we'll look into. F and G's are unknown. The goals are how can we predict whether anything bad is going to happen in this system without a priori knowing precisely what the dynamics are? And the way that we will look into is trying to compute approximations of the reachable set of the system. From where we are and to the extent of our the data that's available to us so far or going further, and the partial knowledge that we may have, and I'm going to comment on what knowledge is going to mean. Again, let me emphasize that we don't know the dynamics. Can we approximate the reachable set? And then the question here is, of course, all the configurations that we might go to, whether they will be intersecting with anything bad in the future. And a question beyond that is, how can we choose a control signal to influence the system dynamics so that we may try to prevent anything bad happening? So these are the two sides. So what is at our disposal here? What is it? Just we have streaming data. We are going with the airplane example. The plane is flying. It's not that we have repeated takeoffs and we try things. We found ourselves in a situation because it has to go on. And then we have the stream data from an ongoing trajectory. And we may have side information and they may include Lipschitz bounds, local bounds on the gradients. Maybe we know partially have partial information on the structure. We may not know parts of the model, but roughly the structure we may know. And of course, everything is still subject to laws of physics, and even trivial structural knowledge that we will see in examples may help, and we will see how it's going to help. As I said, what we try to do is find over-approximations of the reachable set and on-the-fly control inputs. And why do we like to do this setting and the type of work that we have is that as we get more side information, we know more about the underlying unknown dynamics, and our results will get better. For example, this figure shows the pinkish thing on the outside, the outcome for a unicycle dynamics with loose Lipschitz bounds. You can always come up with some Lipschitz bounds. These are loose Lipschitz bounds, and then of course the reachable set. The configurations we may end up at is pretty broad. That means that our chances of staying safe is slimmer. The green one is showing an over-approximation of the reachable set with a little more information. Still the loose Lipschitz bounds, but we also know that there's something coupling in the unknown dynamics that we have, and it helps to tighten it. And if we go and somehow figure out tighter Lipschitz bounds, we can further make the approximation tighter. So this ability of improving the results with more knowledge is very much aligned with trying to use data and partial knowledge toward learning. And then in certain specific senses, we will be able to come up with bounds on suboptimality that we may have out of the decisions. And I think the last one is relatively unique, is that we will have practically useful bounds on the necessary computation. So these will not be algorithms that, yes, they may get really good solutions, but they may never have the chance of being implemented on the fly or on a resource-limited environment, or they may not terminate with predictable computation time. So, okay, let's proceed. When we first faced this problem, at least my own reaction was that, yeah, we will probably not be able to do it if there's such a dramatic change in the dynamics of the aircraft or what can we do. Then we saw these examples that human pilots were able to do these things. Maybe not regularly, but there were examples that it is possible. And this one is from 2003, and the pilot is describing after this happened. They, for about 10 minutes, they sort of experimented. They probably tried some small maneuvers and then figured out how to fly this new object and save the length. And so the first piece of work that we looked into was trying to imitate this. How can we do quick experiments and figure things out? And this is this. The title is Wiggle Wiggle to Differential Inclusions. So how to do some small, tiny, coordinate-aligned maneuvers and apply control inputs, and out of that come up with a differential inclusion that would include the differential inclusion would include the unknown through dynamics, unknown through vector field. So that is the main idea, and it works as I'm going to try to depict this. So we have the data so far, and we have an over-approximation based on the data that we have seen so far and the site information that we have. And as we get more data points or new data points, we have a chance to narrow the corner of that inclusion around where we are right now, and then out of that inclusion of the new data points and the knowledge that we may have, the solutions, constants, etc., go and compute the over-approximation of the reachable set. And there is actually out to some approximation, there is a closed form expression for it. And I'm not going to go through all these symbols, but I want to comment on that. All of these things are just set-based operations. Essentially, we try to keep track of the sets. We try to understand and factor in what the effect of knowing a little bit more on the unknown dynamics would be, how those sets would shrink. And if we get new data points, what the effect of that would be on, again, set-based representations of the cones and over-approximations of virtues. And having said that, so these things are, even though they may look ugly, and they look ugly, the computation of these things can be done very efficiently. With that, so the overall process is going to look something like this. We will go through this thing as the system operates. Unknown dynamics is here. I said that we will try to come up with the differential inclusion with the incorporating this Lipschitz bounds and the additional side information. And I will show examples of what kind of side information I talked about here. It's going to give an over-approximation of the reachable set. So this is now the first part of the questions that I asked. Next is making decisions based on what we have constructed. Taking this predictions on where the system might fall in the future and trying to choose your control inputs, you end up actually having to solve relatively ugly optimization problems, which would not be suitable for online on-board computation. There's some linearization first with inputs. Still, that one is not going to cut. we will end up having a non-convex optimization problem. And what we do is then get into a sequential convexification of the optimization problem and solve a few convex optimization problems, out of which we get an approximate solution. And then once you have the control inputs, of course, you can apply these things in a rolling horizon fashion, and then continue doing these things. Okay, this seems relatively probably complicated, but all these things can be done, despite that the dynamics are unknown and there are certain nonlinearities in it, etc. Can be done relatively efficiently. So I'm going to look toward the examples, but let's comment on can we complete these things fast enough, and we have evidence, both theoretical and empirical evidence toward this. First of all, the bounds that we get are they grow linearly. The computation time grows linearly. The number of flops that you have to execute grow linearly in the number of data points, and this is quadratic in the number of inputs and states that you have in the representation of your dynamics. This is that unicycle example again. The goal here is unknown dynamics. Try to get to the start, the center of this ellipsis quickly. And these are back then completing methods. So I think both dimensions say something here. The horizontal dimension says that shows how quickly, how optimally this unicycle can get to that center point. The alternative methods take significantly longer on the horizontal axis. This is the method that I just described. And this bottom one is if you had known the dynamics, of course, this is not that hard. You can get even quicker. And then the vertical axis is the computation time that is required for these decisions. And again, the optimal trajectory doesn't take any time if you had known the dynamics. But the computation time is significantly lower compared to the other data-driven methods that were available back then. How suboptimal? The suboptimality we can bound with respect to the tightness of the Lipschitz bound and the width of the over-approximation of the reachable set. And this width, we can actually reduce it as we incorporate more data. So this bound reflects on that empirical observation as well. And this compares to, on a quadrotor example, the side knowledge here is bounds on the Lipschitz constants, but then also this trivial piece of information that the speed is the derivative of the position. There is actually, if you think about it, there's no knowledge in that, but incorporating that that piece, structural piece, into your representations buys a lot. And I don't think this is a coincidence, because we have seen similar trends in different settings and in different methods, that unless you tell this, say it's symbolic or structural knowledge into your learning algorithm, it either would take forever or it will never be able to figure it out. So even that is useful. And then these comparisons are with respect to the optimal control that you would have obtained if you had known the dynamics. So the behavior is pretty similar to what the system would have done optimally. We took these things and applied in a ton of Mujoko examples. If you're not familiar, these may look silly, but they actually underneath have relatively complicated dynamics. And all of them follow these kinds of equations. And here we said that we probably would be more likely to know the inertia matrix and less likely to know how the system actually would interact with the world. So we assume that we know the inertia matrix as part of the side information. We have the Lipschitz bounds, and we know that this would also be subject to the laws of friction. And here are a couple of examples. So first of all, I should tell you what I'm comparing to. When this R's means applying what I described. And let me remind you, this doesn't know the dynamics, and it doesn't go and do exhaustive learning or anything. That definitely doesn't repeat anything. It is in one trajectory. You do whatever this algorithm tells you to do in one trajectory, and store that whatever you have done, and compute your performance metric for within that one trajectory. This D4PG, again, this is a couple of years old paper. Back then, it is a reinforcement learning algorithm. It interacts with the world significantly many times. It collects tens of millions of data points and extracts a policy out of that. And then this D4PG is that exhaustively learned policy, how it behaves in the same run that we have for our algorithm that figures out as it goes on. So for this example, this algorithm our algorithm does better for the middle one. It is comparable, and of course, when it comes to more complicated ones, this exhaustive reinforcement learning algorithm finally does better. But I think even first of all, this is not apples to apples on theirs. I think being in the ballpark of a reinforcement learning algorithm while learning only within one trajectory is relatively nice. Here's another example. This is a ground collision avoidance example at F16 modeling. A respectable simulator, 13 states and 4 control inputs. The side information is that we know the rigid body dynamics, but we don't know the aerodynamics forces at moments, how it interacts with the outside world. In the simulation, the starting point is, I think, interesting. The plane is nose down at a relatively low altitude, and we pretend that we don't know the dynamics beyond these bounds, or beyond this side information. And the bottom, at the top one, it figures out how to avoid crash and level the flight. And the bottom one is using some probably naive control algorithms that cannot be simulated, and it is not able to. It's not able to avoid the crash. Okay, so this is that. I'm going to go to the next one, and this one is now. So the first one was within one trajectory. How can we people learn? The second one is not. We don't have this restriction. It is not within one trajectory. We'll go closer to trial and error, couple of runs or millions of runs, etc. realm. But of course, we work on autonomous systems. We don't want to do thousands of different runs or millions of different runs out of the systems. We can explore the world freely, etc. So we want to really do this thing quickly. And I'll get to it. Well, I will give an indication of what quickly will mean. Let me just go through the underlying methodology here. So things are changing, but one way of thinking about learning for dynamic systems is that you gather data and you build a model of a predictor of the states of the state that you have at some time in the future. And this state prediction, you can represent the predictor in many different ways. One way of doing it is building a neural net. Why not? Everybody's building. And then use that, build your loss function, and just use back propagation and train. If nothing else, it is an efficient process as long as you have the dynamic, so the data. But there are some caveats. One is that even the trivialist changes might make your entire learning process obsolete or useless, because in the timing changes, this is built as a predictor for a specific time in the future, and your predictor can become useless. And also, this is not aligned with how we have seen the world or represented the world, or at least dynamic systems, for centuries. So if I wanted to incorporate physics-based knowledge into this learning process, this is probably not the right representation. An alternative representation is introducing differential equations somewhere in this. And now, instead of this neural network representing the one-step predictor, it represents the differential equations, the vector fields, unknown vector field. And then once you have the vector field, you can use it ODEs over and still get this predictor, and then use propagation still. This actually gives a playing ground for a couple of things that we wanted to see whether they could help or not. One is if you know some parts of your dynamics, or if you know structure, let's call that given buzzword as physics-informed structure. For example, here the red pieces are unknown still, G's are unknown. Some parts of the dynamics are unknown. Nevertheless, how they come together and build the dynamics, the structure of it is known and it's included in that. In those cases, instead of trying to figure out a one big neural network, you may be able to structure it to constrain the learning to smaller pieces of it, and then put it together. So that's going to be this physics-informed structure. I think the other piece is actually also important, if not more important. In many cases, even though we don't know the dynamics, we may have partial information. I gave examples in the other project on partial information. Here's one more. You may not know the exact contact forces with the environment here or workspace, but whenever there's a contact, you will know bounds on the contact force. At the least, they will be non-zero. At least because of the friction, there may be relations between the components or the magnitude of the components, or other pieces of information. So let's gather these things into these inequalities. And this picture shows now what our data looks like. The blue comes from the actual data collection of the system. You run the system, you know how in that specific configuration the system is going to operate. So let's call that the training or labeled data. Blue is just the conventional data that we would collect for learning purposes. Red is made up. Red is just a sample in the workspace, in the configuration, possible configurations of the system. So we don't know how the system actually is going to behave there. But if this is a physical system respecting the constraints that we have, then wherever these points are, they will also satisfy these constraints. So they are not labeled, but we know something about that. So we'll try to use that in this process. And for lack of a better way of doing it, it is just going to be some penalization of the violation of those constraints of those sampling points. And then the overall thing is going to be still amenable to backpropagation. So all these tools for training we can use. And then there are two pieces again, this physics-informed structure and physics-informed constraint. Hence the title of the slide. Okay, so again, there are some simulation examples for this, but this one is two former grad students, Frank and Cyrus. They are playing with this drone. Frank flies it, and they will do a couple of runs here. They will essentially fly this thing for in total of 3 minutes. And then after that, they will go and they will use the data that they collected. That step is going to take about 15 minutes as well. And then they will bring what they learn, what the algorithm learns, and implement it on this drone without Frank flying it. If the drone is going to fly by itself. And a couple of comments, again, 3 minutes of data and up to 2 meters per second speed, and the Euler angles are about up to 20 degrees. I give these numbers because when it comes to testing these things, this Quadrotor is going to, seems like it says 6 plates. This drone is going to be able to fly beyond this training regime. And they use their dynamics, what they learn in a MPC fashion. This one actually it goes beyond what I described. It tries to figure out a stochastic differential equation, but the underlying ideas are very similar. So they figure out some model for the system, incorporating data and side knowledge that they had, and then they are able to use their model in MPC fashion after 3 minutes of training and training data. And then about 15 minutes of computation, they are able to put this on the drone and it flies by itself. Frank went and did an internship at Toyota Research Institute, and then he continued. He's now an assistant professor, and I hear that he has collaborations with Toyota Research Institute. He might have an access to a full-scale car in his lab. So this is on an actual Supra wired for driverless driving. And the challenge here is this, that tire modeling is relatively hard in all aspects of it. And there's a desire to do it from data. Merely from data had turned out to be complicated. And Frank's approach was, of course, just merging these site knowledge and data. And again, he was lucky enough to sit next to a professional driver who had to pull some relatively aggressive maneuvers here, again for 3 minutes, and they push it through this what I tried to describe, is the outline, and after that they were able to put this on the actual vehicle without the driver driving. I'm guessing the driver was still there, and they were able to pull this autonomous drifting maneuvers that are at the edge of stability boundaries. So they are not necessarily some mild maneuvers that you would expect from an autonomous vehicle. And we believe that incorporating site knowledge was influential in these things of autonomous. Okay, so that is, I'm guessing that is the end of the second piece. So I'm going to now continue going, and if you see a trend here, the first one was in one run, very localized knowledge that you might want to incorporate with external data. The second is you want to limit the data collection, but it is not as severe as the first one, and it is still a relatively low-level maneuver. It is not that the autonomous system is trying to make a tactical decision or a high-level decision, faces changes in the environment, and tries to follow rules, etc. But just there are low-level constraints that it had to follow. So now I want to move towards this higher-level view where we might be subject to more interesting constraints. The environment might be more dynamic, or changes might happen in that. What will we do? And this is really now transitioning toward this connection between learning and formal methods from core learning and controls like functions, the first one or two. So we will, let me go back. So I have this California driver sample with the driver book. So the point here is that if we have a knowledge source of that, right, how can we represent that and factor it to our reasoning? I use a little example. Of course, this is not the California driver sample, but flavor of a example of a traffic rule. So we have this example workspace here. There are two types of roads. The gray ones, you will call them priority roads, and the white ones, the vertical ones, are ordinary roads. The goal here is that this car goes from point A to point B, and it respects these traffic rules. If it is traveling on an ordinary road and comes to a intersection, it will have to stop for a while. In this case, to keep it simple, for one time step. And if it is traveling on a priority road and comes to an intersection, it doesn't have to stop, just proceed. And the next question is, what can be used to represent this kind of knowledge? If you are familiar with automata-based representations, that would be a good working model for the next couple of steps. Connecting to reinforcement learning, there was a jargon there that people called reward machines. This is actually glorified finite automata to keep track of what are acceptable or possible behaviors for a system. So let's call it a reward machine, and it looks like this. it essentially, again, includes all possible ways of doing this while respecting the rules that we have here. I'm going to walk you through one possible way of doing it, just so that we stay with it for a few more minutes and might try to build some intuition. So the way that it goes is that we start from here, start, and the system is starting here. So there's going to be an association behavior here and what kind of transitions we take the bottom right side. So the car is going to proceed. It is on a priority road. It proceeds, comes to an intersection. It was on a priority road. It stays on a priority road. So there's a self transition here. And now it proceeds. It was on a priority road. It stays on a priority road. There's one more self transition. And these are color coded. Now it wants to make a right turn. But once it makes a right turn, it's going to transition from a priority road to an ordinary road. So that is this transition. It comes to an intersection. Now it has to stop there, and it's this transition. Now it is transitioning from an ordinary road to a priority road, and just making a left turn. It comes back to this state. And these V1, V5, etc. These are just abstract names of the events. But there's not much of a meaning to it. And now it arrives at B, and it goes to the state. So this vehicle was able to go from A to B, following the transitions in this and arriving this special labeled state. That means it complies with everything that we see here. So everything is legitimate, and coming to this specially labeled state is that we have achieved our goal. And as you can see, there are tons of other ways of actually transitioning in this and reaching this special labeled state. That refers to that there are tons of other ways that you could have achieved what we just did. So a reward machine is going to encode all possible ways of doing this thing. And if you look at it, this is the overall task that we have, goal and constraints. And something like this tells us what are these subtasks we might implement and patch them and accomplish our overall goal. So it is going to serve this representation for possibly decomposing the overall task into subtasks, and that's going to be useful. That's going to help in reinforcement learning. And reinforcement learning is coming up with a representation of a policy, agent interacting with the world, doing something, seeing what happens, and based on that, updating its policy or intermediate representations that help you build an optimal policy. I'm not going to get into those details. And the way that reward machines will come is, again, it is going to chop this thing into pieces. Instead of having one reward function or a policy for this overall task, we'll try to come up with multiple subtask policies, and then reward machine is going to tell us how to patch them to be able to comply with the higher level of constraints that we have. And there are tons of examples in the literature, including our early work, that if somebody gives you a reward machine of this sort, you can incorporate it to reinforcement learning and take advantage that you don't have to learn everything all together and improve the data efficiency and get other benefits out. The one result that I want to present next is building on that, but it knows that there is an underlying task. So there's a structure into what you are doing, but there's not necessarily a reward machine representation of that availability. So we will start with loaded information or no information about this reward machine representation, and iteratively build it while running the reinforcement learning. So we call this joint task inference and reinforcement learning. And as I said, it will start with a trivial hypothesis. But this automaton essentially doesn't include any knowledge. It would say everything it sees, all the sequences of events it would see, it would say, yes, that's good, that's good, that's good. And then there's a way to incorporate any reward machine into reinforcement learning from the previous work. So you take it, and now the agent does something in the world, and other loop compares what the agent sees in the world to what the reward machine encodes. And inevitably, it will be almost trivial to find. No, I'm going to take that back. It's not going to be true. It is plausible that you will see things that do not comply with the knowledge encoded in this trivial reward machine. And once you have enough evidence that this reward machine is not necessarily capturing what you are experiencing, we will go through a automaton learning type other loop and create one more reward machine. This reward machine is going to not necessarily be the representation of the actual test that we are implementing, but it will rule out the behavior that we have seen, the sequence of events that we have seen that did not comply with the previous reward machine. So it's a little bit more faithful representation of what might be happening underneath the example. So we bring it down here, reinforcement learning continues. Again, we see things that are not compliant with this representation. We take it back and continue and try to build a more involved reward machine. You can run this, continue running this. We know that we will converge to a representation of the reward machine that would accept the same sequence of events that would be accepted by the true unknown reward machine. Okay, with all that, I'm going to skip the next slide because even though there are some theoretical results here, they are not that insightful. Let me move on to some examples. So what's happening here? This is that two by two roads example here. The text says that there's improvement in data and more reliable conversion, etc. So this bottom three plots are three baselines back then. And the higher is better here. One is what we can expect out of this entire exercise. One is the optimal performance level. And with these baselines, these two of them never see any useful information, and they never actually they never did anything useful. This one is sees something, it tries to explore, but as you can see, we would call this thing as a reliable convergence to the optimal performance level. It struggles quite a bit after 2 million training steps. This one does what I just described, this back and forth. Early on, it spends the effort more toward figuring out the task knowledge. And then as we go along, it explores a little bit. And I would say very quickly then, once it starts getting a little bit of an understanding of what the underlying task structure might be, it very quickly gets to the optimal level. And then, of course, we played with this. This figure shows that we don't start entirely from scratch for the reward machine. We had pieces of it, whether that would help, that would expedite things, and it did. And this process actually, at least in some examples, we were able to see that we somehow accidentally encoded incorrect task knowledge into the reward machine. We would be able to actually find it out and pull it out and then proceed with the algorithm toward figuring out a reward machine that would, again, accept the same runs as a grunt that might comply with the task that we have. Okay, so that's the end of it. Let me just make a few comments on the next piece of knowledge and how it might come. And this one is going more toward compositionality. And there might be multiple reasons or ways the compositionality, and I'm going to call this structural knowledge, might be relevant. One, because of the structure of the underlying workspace. A robot, even a single robot, may be able to decompose the tasks, assess its risk locally, and patch them together. Or if multiple agents are working in the same environments, even though they probably see them as multiple agents, because they would have to rely on each other, interact, etc. So it is a coupled operation. But in many tasks, that coupling is probably sparse. They interact probably only at certain times and for certain purposes, and then they go their own ways and do whatever they need to do, and just the overall team level task is accomplished. I'm not saying all multi-agent tasks or all spatially distributed tasks for individual agents will lend themselves to such compositional structures, but I think that there are sufficient many of them to for us to more seriously think about compositionality. And I'm going to show a couple of examples. So this one is there are 10 agents. Each of them starts from where they start, I think, and then each of them have their own goals at different places. They have to, though, come together and agree on something. There's a rendezvous location first. They need to come and be there at the same time and then go to their respective locations. So it might sound easy, but it is actually like searching a needle in a haystack, because this is 10 agents, even in this size of a workspace. Their entire workspace is the Cartesian product of this, and then there's coordination between them, etc. So yeah, all of them come here and then go to their respective locations. So what we tried to do was, how can we decompose the training task for each agent, that each agent trains separately in the workspace, individually in the same workspace, and do their training. And we want them to be able to bring what they learn and implement them together, and then have their team level task complete. And we try to do this in such a way that the reward machines, as I discussed, we decompose them and modify them so that we introduce these coordination signals for each of these agents separately, so that they can go to do the training individually, but when they come back together, they will be receptive that they will be working with the other agents. And what we did was, just as I said, we decomposed the reward machines, one for each agent, modify them with these coordination signals, and in such a way that when these reward machines are composed, they are bisimilar to the team level reward machine. And then we come up with a way to individually train these things with these added signals and then put them back together. And here are some examples. I think this is this 10 agents example. These baselines, in this figure, low is better. These two agents, these two baseline algorithms cannot figure out anything. And then doing it with this independent distributed training and then putting them back together is this curve. And for the reason I actually alluded to, this trying to run a learning algorithm for 10 agents all together and them not getting any improvement is, in retrospect, not that surprising. Because if you run these 10 agents, the chances are that they will do anything useful is very low. And until you see some improvement in what you do, you don't get any signal for improvement, for reinforcement. And then it becomes just a pure chance, and the state space is so large that the chances are pretty slim. By separating and instilling the need for coordination later on, makes it much more likely that through exploration you will see something that is useful. Okay, so and I should probably comment on that. If we do this thing with, for example, 3 agents instead of 10 agents, these two algorithms were sort of figuring things out much more slowly, but making a little bit more progress. When it comes to 10 agents, then these exploration and figuring things out all together becomes much less. Hence that they get stuck. Okay, this is a single agent, but I want to make a couple of comments on this. This took a lot of time, and then we are building on this in several projects these days. This is now, as I said, simulations, but there's a workspace here. And this is a demonstration at the Army Research Lab testing grounds in Maryland at Grace's quarters. There's a workspace, and there's a natural decomposition of the different parts of it. So we can take that decomposition, and instead of trying to learn one policy for the entire environment, we can try to learn how to do things in one part, another part, etc., and then patch them together for a given task. So we did that, and then the demonstrations were good. Then the main use of this kind of thinking is, I think, not in nominal conditions, but under off-nominal conditions. What we did was we blocked this road here. So now the agent needs to figure out what to do. And it figures out that, you know what, the controller that I had trained for this piece is not useful anymore. I need to figure out how to go around this. And there's a hierarchical strategy here. So the higher level figures out, let's go around this area now. And of course, this part of the operation are still relevant. It is just that this one controller that was responsible for this area, and it became obsolete. So this way of thinking hierarchically and compositionally helps figure out where the issue is, and then helps also focus on a much smaller task than the overall task, and more easily updates what needs to be done. So indeed, in this case, it was possible in a few hours run this thing a couple of times and then simulate in tandem, and then come up, revised one of the subcontrollers that we have, and much of what had been learned was reused. A specific place was revised, and in this off-nominal configuration, the system was able to still complete its task. That was the last result that I wanted to show. A little bit of a summary here. There's no reason for a summary. I have the hypothesis. Hopefully, I have shown sufficiently many examples that physics-based knowledge or contextual knowledge or structural knowledge can buy a lot for us if we have to rely on learning for decision making in autonomous systems. And I'll skip this slide. A couple of newer things that are growing in the group is making more connections. For example, connections with information theory is helping us to look into how we can install or develop capabilities for autonomous systems for them to create strategic advantage for themselves by minimizing information leakage or trying to mislead the adversaries around them, and connections with these foundation models, generative models, or large models, etc. I think it introduces tons of new opportunities for designing, verifying, and deploying autonomous systems. And it is making connections with pretty much all pieces that we have in our work. And even I haven't made a connection here, but these could be connected to each other because, of course, how an autonomous system interacts with the rest of the world, I cannot imagine a medium better than language for such interactions. Excellent representation of knowledge and information for interactions is language. So with that, I'm going to stop, and if there are any questions, I will be happy to answer.
Thank you, Dr. Topcu. Yeah, it was a wonderful talk, and we have a couple of questions. I'll just relay them to you now. So the first question is, will the over-approximation of reachable sets make optimal solutions too much conservative with respect to safety constraints?
So there is a conservatism there. I'm not sure what safety constraints means, but inevitably there's a conservatism. There's too much unknown. Yeah, let me just stop there unless there's a follow-up.
Yeah, I don't think there's a follow-up. And the next question is, it's about data collection. Like, the question is, I'm wondering if covariance distribution that happened in data collection will affect the results, the ongoing results in the future.
So I think they would, and it deserves more work. And as it is probably not that hard to see, but I did not comment on anything about the quality of data, right? I have made the assumption that data is comes as it is needed by the algorithmic methods underneath. Yes, I think noise in data, the rate of data, availability of data, correlation in data, etc. All those things might affect a lot of things that we do here. Hard to give a unified answer to it because it's going to affect every piece differently. But yes, that would require a lot more discussion. But it is a good observation.
Yeah, there are more questions, but if you have time, I can ask the rest of the questions. Just
Oh, I have to.
yeah, sure. Yeah. So, just a second, sorry. I think there is some issue with the noise. I'll be back in a second. Yep. Yeah, in slide 7, it seems like the general system is in the control affine form, and the question is, how would you handle if it's a nonlinear function and if it's not affine in general? Like, how should one approach that kind of system?
Even though this shows that dependence on it could be polynomial on the control. This is actually control. I would call it control affine as well. We need to commit to a representation, and let me, in general, I don't know, but let me make a distinction here. That the claim here is not that the underlying dynamics is in this form. Who knows what the underlying dynamics are? The point of this is that we try to come up with an approximation, and we choose to represent it in this way. This approximation of the dynamics is not correct, and it is not even necessarily a universal approximation. Based on the data that we have seen here that we are operating, we just need a representation that we can quickly compute and make a decision off of. And what we learn here has no relevance for what the system might do in a different part of the state space, or what the system would do if it got to fly again. It is just for this time very local, just for the purpose of survival. I should have emphasized that the point of this project was survival, just saving the day or saving the moment. And we never came to it, but also I think equally, if not more interesting question is figuring out that you cannot save the moment and crashing in a graceful manner. So the goal here is not figuring out what the actual dynamics of the system is. All right?
Yeah. And the next question is, yeah, they're thanking you for the great talk. And most of the examples involve static environments, and they're wondering if what would happen in a dynamic environment under the same situations, like when dynamics of the system itself changes, but the environment also changes over the course of time.
I think that's the answer is actually clear, that we will have to look into other models and game type interactions will come. I agree. Some of these things may serve as building blocks, or we may need to look into entirely different problems and representations. If I don't know who's asking the question, but if they want to reach out, I will be more than happy to discuss. This is just one sliver of work that I presented today, and the group has a lot more in looking into such interactions. I will say though that if there is such changing environmental conditions are interesting. We would need to look into different problems. I wouldn't take what we have, for example, in the first piece of the work and ask how that can be extended to strategizing against an adversary or multiple of them, etc. We need to have a hierarchical view and cut and study sometimes problems in some specific layers where such interactions are more relevant and more manageable for study. More than happy to discuss offline.
Thank you. The next question is, in the context of using physics-informed neural nets for prediction within MPCs, there might be an accumulation of error over time. Do you have any thoughts? How could this be handled, or if it's negligible?
Oh, it is not negligible. It definitely accumulates. But then it has nothing to do with neural networks or any other thing, right? Just as long as you have an approximation of the underlying dynamics, which is everything that you do is going to be, even without learning, there's going to be an error accumulation. I don't know, just what other ways make your model a little more accurate, but there's no end to it. Make your prediction horizon smaller, or as the implementation of that neural networking did, we'll see the world a little bit receding horizon fashion and take some corrective actions. The modeling that we did only looked into the first piece. How can we make this model a little bit more accurate with whatever we can use? The implementation of that try to take advantage of that receding horizon. Thank you.
And the next question is, in page 25, how can we define, or like, how is the state space and action space and the reward is defined in practice? Because all of these have a great influence when it comes to the computational burden.
The reinforcement, okay, actually, okay, yes. So the reinforcement learning takes place over a continuous space, possibly continuous action, I don't remember, in this working environment. The top level is these discrete events, where in the road, which event has happened, what are you going to do next? And that is discrete represented. I'm not sure if that is the question, but yeah, that's all I can say with this much percent of the question.
Okay, thank you. And the next question is going back to data collection. Like, what are the requirements on how you gather the data online so that the autonomous run works? Example, minimum duration / the amount of excitation or exploration, all of these notions.
So let me start with the part which comments. There is something that resembles excitation. With these coordinate aligned inputs, essentially try to excite the system in different ways and hope that it's going to reveal information to us, right? There is no, as far as I recall, there is no result that says if you excite it this much in this way, you will learn the underlying dynamics. And there's a reason for it, because again, the purpose of that project is not necessarily learning true dynamics. This is coming up with a representation that will be useful locally right now. There is no claim on that what we learn is the true dynamics. And there is actually no even desire, because let's face it, if an airplane loses one wing, nobody's going to ever use it again. The only thing that is expected is do something so that you land properly or crash properly. So in that sense, the classical system identification and excitation results, we did not even think about that. We a little bit looked into what if we had noise in the data, and just noise in sensor measurements turned out that of course introduces additional error, but it does not break the results. We have not looked into what if you actually lose sensors or other very relevant concerns that you may have about data collection when it comes to learning. We have not looked into that.
Again, there is one more question. Could you comment on the safety guarantees of autonomous systems when incorporating learning-based methods into the formal method framework?
Sure, that's a general question. So I think that we have, in many of these examples, in many cases, we have a system, and it goes through events, states, configurations. There's a clear notion of a trajectory. In that sense, characterizing the safety of such a system is no different than characterizing that for a system that has nothing to do with learning. But how you can verify whether that system, how you can predict whether that system is going to satisfy under all configurations, etc., that becomes much blurrier, or even not blurry. It is still a valid question, but how you will do that algorithmically with the limitations on the knowledge about the outside world, on your understanding of the underlying dynamics. So I think the characterization is not that unclear, at least in my mind. But how you will do it is the elephant in the room.
And I have a question for my friends. Like, when it comes to these reward machines, when we're iteratively learning them, I'm just curious that like one may not be able to learn the exhaustive reward machine. So how much does, let's say, the inaccuracy in the learned reward machine and the ideal reward machine propagate into the decision making? Is there a mathematical framework that's already there?
But you mean somehow there's a ground truth reward machine, and there's one that is not exactly that hopefully relevant. Whether if we had known these two, can we translate that into a bound on the performance?
Something similar to that. How does these iterations and how we make these iterations affect performance at the
So predictably, I don't know how to do that. How to go from a in quotes distance between the two reward machines to performance. I don't know. I feel like one, if through some, I don't know, by approximate by simulation or simulation relations, you may be able to come up with some sort of these characters, a way to think about that. I'm not familiar with that. Yeah, and very good those, to my surprise, even partial knowledge seems to help, as those examples shows. Theoretically, I don't.
Okay, yeah, thank you. And one more question, sorry. So when it comes to having these over approximated sets and shrinking them based on more data, I'm just curious what mathematical framework is used. Like, is it concentration inequalities, or how do we?
There's nothing stochastic in this version that I described.
Okay.
This is going to be, as I said, set-based operations. I'm very sure of sets. And if you have a data point, you essentially like data and knowledge. It just chops off the parts of the set, and you try to the representation of those sets. Once new constraints come, is easy to propagate, incorporating the knowledge of it.
Thank you so much. I think that's all the questions we have for you. Yep.
Nice questions, and I enjoyed. Thank you.
Thank you so much.
Yeah, everybody.
Yep. And all right, everyone. See you next week. The edited video will come out in a couple of days. So, yeah, keep a lookout for that. See ya.